Okay, guys, learning target number 2. Learning target number 2 focuses on the Doppler effect. Now, something I missed. I can't believe I forgot. To add it to your notes, it's in the slides. It's a standing wave. Okay. And then in the slides, it gives a definition of a standing wave. And basically, it's a wave that reflects back over and over again. And it aligns, so we have both constructive and destructive interference, and it gives the appearance that the wave is not traveling through the medium. So that's what a standing wave is. Okay. Now the apparent change in frequency due to the motion of the source or the receptor is called the Doppler effect. Okay. And so what we mean by that is if something is moving towards or away from you, it can change the frequency that's being produced. Okay, so here's the example that we have here. Now let's give like a precursor situation. So before this is happening, what if we have these two people, they're standing on the sidewalk, and then we have the police car in between them, but everything is stationary. And the police car is going to turn on the siren, and so there is sound being emitted. Oops, that one went too far. That's okay. There's sound being emitted at regular intervals, right, from the siren. And so in this situation where everything is stationary, the waves aren't compressed or elongated, and so the sound of the wave to the person in the car and the two people standing all stationary, it would all sound the same. It wouldn't be really high or really low in pitch. Okay, but as soon as we either move the receptors or the object producing the sound, the source, then we can create a Doppler effect. So now, after it's stationary, the police car is going to now move this direction. And when it does, it compresses the sound waves up in front and it elongates them in back. Okay. And so what happens here is we get compressions of waves, so we get shorter wavelengths. It's still sound, so it travels at the same speed through the air. We're just compressing more wavelengths into a smaller amount of space. So that would mean higher frequency, like the frequency is a larger number. And when frequency is high, then pitch is high. It sounds high, okay? When frequency is low, as in the number for frequency is lower, then the pitch is lower, okay? It sounds lower. That does not have anything to do with the volume, okay? That doesn't mean that we hear it louder or softer. It means it's a higher pitch or a lower pitch, okay? So when the source is moving towards someone and these waves get compressed, we get higher frequency, which then results in a higher pitch being heard. So something I want you to be aware of is the relationship between pitch and frequency. Okay, so when frequency increases, pitch also increases, so that would make it proportional. Or vice versa, right? If pitch gets smaller, then frequency will be smaller. Okay, so when one goes up, the other one goes up. When one goes down, the other one goes down. When the object is now moving away, then on the other end, our wavelengths increase, and so we have less waves per given time frame, and so the frequency lowers, so the pitch lowers. Okay? So I want you to give a couple sentences describing what's happening with the Doppler effect. Explain how you and why you hear a higher pitch as the car travels towards you, and why you hear lower pitch as the source, in this case the car, is traveling away. Okay, bow waves. So when a wave source, whether that's a sound wave or whether it's like a water wave, if it moves faster than the wave that it produces, then it creates a bow wave. Okay, so like let's think of a boat on a lake and it's just kind of going to bob back and forth. And so if it was stationary, it would just give concentric rings around the boat, right? But now the boat's going to start moving forward, but the velocity of the boat is going to be less than the wave that it's producing. Okay, and so we have the boat and it creates a wave, right? And the boat's right in the middle, but now it's going to move a little bit and it's going to create another wave. Then it'll move a little bit and it'll create another wave, right? And so as it's moving velocity that way, we compress the waves on one end and we elongate them on the other one, just like we saw with the Doppler effect. Okay? If the speed of the object is equal to the speed of the wave, so that would mean that we create a sound, right? And so we get this sound wave. And then when we're on the cusp of that sound wave, because we're traveling at the same speed as that sound, or let's not talk about sound yet, of the wave, the water wave, like with the boat, we're on the cusp of that water wave, we produce another wave. And then again, this is going to continue, right? And so the object will remain on the crest of that wave that it's producing. Okay? So that's when the velocity of the object is equal. Now, when the velocity of the object exceeds the wave that it's creating, so it's like we have this object, okay, and it's going to create a wave, but then it's going to exceed. It's going to go faster than the wave that it's creating. Okay. Then what happens is we get something called a bow wave, and it's this V shape that occurs. Okay. In the concept of a boat that's traveling, you could think of it as the wake that's created when the boat travels faster than the waves that it produces. And as you increase in velocity, you decrease the width of that wake. So here's what I mean. Let's say, same as before, we're going to travel faster, but we're going to travel even faster. And so here's our first sound wave, right? We're going to travel even faster, further away from that one, similar, and then even further. And so what we end up with is, oh, I didn't draw that V very well. We end up with a narrower bow wave there. Okay, supersonic, super greater than sonic sound, so traveling at a velocity greater than sound. And just a reminder, and if this doesn't come right to mind, make another note of this. Sound travels through air at 343 meters per second. Okay, so an object traveling faster than that. Okay, shockwave. Shockwaves occur when an object moves faster than the speed of sound. Okay, and so what happens is these sound waves, they kind of all gather up on top of one another because the object's moving faster than the sound wave that it produces. And so then when this part of the cone, it hits the ground, you kind of hear that sound almost all at once. And so that's what a sonic boom is. Now, there are a couple videos in the slides, okay? And I will, if the videos aren't working through Nearpod, I'll make sure that I put the separate slides below so you can access those videos. It's important that you watch those. The first video is a description of what a sonic boom is, and after you watch that video, I want you to give a couple sentence description of what's happening there. Okay. What I like about watching the video is that you can see animations of like how these things are produced, and I think that's really helpful. And so I want a couple notes taken there of the sound wave. Okay. Yeah, time-wise. So that is learning target number 2 about the Doppler effect, okay? And so now learning target number 3, we're going to analyze this bow wave a little bit more closely, and there's a couple of equations that go along with this. The first thing to recognize is in these equations, it drives me nuts, but it's just the way it is, v sub s is not velocity of sound, it's the speed of the object. So please, please, please be mindful of this when you use these equations, that v sub s is the speed of the object, and v is speed of sound in a specific medium. So if it's sound traveling through air, then again it's at 343 meters per second. Okay? All right, so first equation that I want you to be aware of is Mach. Okay? So Mach number is a comparison of the speed of the object compared to the speed of sound. So if their speed of sound through air is 343 meters per second, and an object is traveling at 343 meters per second, that would equal 1, and so they'd be traveling at Mach 1. Okay? If we have anything greater than that, we have over Mach 1. If we have anything less than that, that would be subsonic, and we'd have less than Mach 1. So that's the first equation. The other equation is this half angle equation. So we call this the Mach equation. Then we have the half angle, which is sine of theta is velocity of sound over velocity of the object. Okay. Let's see. So for this, let's derive where this came from. Okay. So we're going to create this kind of image here, saying like the object is here and it creates a sound, and that sound travels, right? And put that more in the middle. And then we're here, and the sound travels. And we get our bow wave, right? Okay. These dots represented the location of the object, right? And the circle represented the distance traveled by the sound. So this object started here and it ended there. Okay. So that's just a distance, right? And there's a couple ways we can describe distance. In this situation, if we know the velocity of the object multiplied by the time, then that will tell us our distance or displacement. Okay? And just to kind of double check that, velocity meters per second multiplied by time in seconds, we're left with meters. Okay? So I'm going to represent this line, this distance or displacement, by velocity of the object multiplied by the time it took to get there. And we have a similar situation going on here. If we're going perpendicular from the edge of this circle to the center point there, where that's my right angle, perpendicular to the edge there, okay? This distance traveled by the sound happened in the same amount of time, so we can have a very similar justification that this would be velocity of the sound multiplied by time. If this is the entire angle, the half angle would be right there, right? So that's why this is called the half angle equation. So that's the half angle. If that's my right angle, then here's opposite from that. So that's the hypotenuse. Here's one of the legs. Here's one of the legs. So a reminder, sine is equal to opposite over hypotenuse, which in this situation, opposite from this angle is velocity of sound multiplied by time, and hypotenuse for this angle is velocity of the object multiplied by the same amount of time. And since time is on the top and the bottom of the equation, we can cancel it. So then we're left with our half angle equation of velocity of sound divided